So this video is covering this idea called work energy theorem. I don't know that you noticed when we went through the work notes and the energy notes that both of these values are measured in joules. So the equations are different. Work is force times distance, but those have to be parallel to each other. And energy is different based on the type of energy. It could be mass times gravity times height. It could be 1/2 mass times velocity squared. They're different equations, but they're measured using the same measurement value. How or why is that possible? The answer is they are directly related to each other. So just as an example, let's say we lifted a box straight upwards. The force was applied in the same direction that the box moved. So the box was lifted this distance and the box is now up here. What kind of energy did that box just gain by being lifted? Work is definitely done. That force and that distance are parallel. But what kind of energy was just gained by that object? The answer is gravitational potential energy, because even though that box was moved a distance, it was also lifted to a height. These two values would be the same, but however you look at it, they're just different ways of looking at the same idea. It gained potential energy. Where did it gain that gravitational potential energy from? Well, from that work that was done on the object. That work, that force and that distance, lifting that box up, gave it potential energy. So this idea is just that however much work you do is exactly equal to how much energy is gained or lost by the box. You could take away energy, like if I'm stopping a moving object, I am applying a force and moving that object a distance, or that object is moving a distance, and taking away energy. So there's an equation on your formula sheet that it looks like a math equation, but you're maybe gonna use it a little bit for math. You may not plug numbers directly into it. It's another one of those idea equations, and it looks like this. Work is equal to any change in energy. It can be an energy loss or an energy gain, and it could be any type of energy, kinetic, potential, electrical when we get there. But any change is directly equal to how much work was done on that object. So let's look at a few different examples. These slides are going to kind of be repetitive, but it's just to hammer that point in. When an object is lifted to a given height, work is definitely done, right? This person is applying a force upwards, and that box is moving an upwards distance. Those are parallel. Work is being done. The key here is the work done on the object is now exactly equal to how much energy was gained, in this case, gravitational potential energy. The part of this where people struggle with is that you kind of have to make your own equation with this. And I know a lot of people don't like that, but again, this idea comes in handy right here. Work equals the change in energy that you see. In this case, we're seeing a gain in gravitational potential energy. So what I could do is I could set work equal to mass times gravity times height. I could also set gravitational potential energy equal to force times distance. And in this case, maybe you'll remember from old work problems, I would actually make this the force of gravity you're having to overcome. The equation for force of gravity is mass times gravity. These are basically the same equation, which kind of makes sense that they're directly related. Again, you're going to plug in different things based on what you know. So let's try an example of this. This example is going to seem really, really scary, especially when I draw it out. Don't panic. I have a way around it. So a 185 kilogram refrigerator is loaded into a moving van. We should still label stuff we know, be in that habit, by pushing it up a 10-meter long ramp. I'm going to say that's a distance at an angle of 11 degrees at a constant velocity. Still be in the habit of underlining all that. How much work? A little typo. How much work is being done? So we are looking for work. So I always like to draw a picture, especially when there are angles involved. So the ramp has an angle of 11 degrees. Oops. And the distance the refrigerator is pushed, this distance right here, I'm just messing up all these things, is 10 meters long. And we know the refrigerator eventually makes it to the top of the ramp, and it is a 185 kilogram refrigerator. Excellent. So typically how we figure out work is equal to force times distance, and that force has to be parallel to that distance. Since this distance is along the ramp, the parallel force doing the work is the force applied by the movers. But the problem with this force is we don't know this force. The only force I think I can calculate very easily is the force of gravity. And those are definitely not parallel to each other. I do know the box is moving at a constant velocity, so F net is 0, so all my forces are balanced. So I know the normal force is perpendicular to the surface, but that still doesn't help me figure out this applied force. So now I'm going to show you the scary way we have to calculate applied force. And again, I actually wouldn't use this method, but I'm just going to show you if you get stuck, this is what you would have had to do. So force of y, you would have to break this force of gravity into its x and y components at an angle, and then this weird x component right here would be exactly equal to the force applied. And that's gross, because we would have to know this angle, we would have to just do some complicated stuff that honestly we're never going to do in this class. This is like a pre-AP, AP style problem. So I want you to forget all of that. I want you to just think, well, I don't know force applied. Is there some other way I could calculate work? And that's that equation that we just learned. Work is also equal to the change in energy experienced by the box. What kind of energy did that box gain by being pushed to the top of that ramp? The answer is it gained a height, so it definitely gained gravitational potential energy. So I could say that work is exactly equal to the amount of gravitational potential energy gained, or I could say work is equal to mass times gravity times height. I just replaced this with its little equation that it's made up of. The good news about this is I know the mass. The problem gave it to us. I know g is the acceleration due to gravity. It's 9.8 always. And I can actually calculate the height fairly easily. Since I know the hypotenuse of the triangle is actually this distance, this side of the triangle, I can calculate the height, which is the opposite side of the triangle. So I'm going to go back to trig, everyone's favorite. Since I know sine, or I'm going to use sine since I know the hypotenuse, and I'm looking for the opposite side. So sine of theta equals opposite over hypotenuse. And I'm just going to plug in stuff. Sine of 11 degrees is the opposite side, which we labeled as h for height, not hypotenuse. And then the hypotenuse is 10 meters long. I am going to multiply both sides by 10 to get that height by itself. And height is equal to 10 times my sine of my angle. So I get that the height is 1.9 meters. So now I have enough information. I can plug into this work equation. The mass is 185. That problem tells us that. Let me make this a little less big. And I know acceleration of gravity is 9.8, and I'm smushing this all in here, I apologize, but you're multiplying all these values together. So 185 times 9.8 times 1.9. I actually get that the work is equal to 3,444.7 joules. Again, that work is measured in joules. I know this is all over the place. But this answer that's written right here is what you would round it to, except I think it's a little off. We should round to sig figs, and it looks like all my numbers have 3 sig figs, so I should have actually rounded this to, I would say, 3,440 joules. Or, yeah, that's what I would have rounded it to for 3 sig figs. But we're not going to take off for sig figs, so just something to keep in mind for maybe future science classes. So I know that looked scary. But really, if you paid attention to this part made it easier. So I didn't have to find the x and y components of that weird force at an angle. I know the work is equal to the gravitational potential energy gained, and I can find the height fairly easily. Let's try a different example. So in another video, we talked about if you get an object to start moving, you are also doing work. For instance, this guy applied a force. This ball is moving a distance in the same direction, definitely work being done. And how you are giving the ball kinetic energy by doing work to the ball. So how much kinetic energy gained by the ball is exactly equal to how much work was done on the object. And again, this means that I can set these individual equations equal to each other. I will kind of build my own equation based on the information I have. So for example, 5,000 joules of work, they are telling us that this value right here is work, was done to stop a 100 kilogram football player. What was the player's initial velocity? We are looking for velocity initial. So typically, I know work is equal to force times distance, but they give us a value for work. So I'm probably, and they don't give us force, they don't give us distance, so I'm probably not going to use that equation here. But I do know work is also equal to any change in energy you're experiencing. This football player is coming to a stop, so he is losing kinetic energy. So I know how much work was done on the player is exactly equal to how much kinetic energy was lost. So I could say, I know the value for work. I'm not going to replace it with force times distance, but I do know the equation for kinetic energy is mass times velocity squared. So now I have an equation with everything that I have and what I'm looking for to solve. So work, I'm going to start filling it in with numbers right here, is 5,000 joules equals 1/2 times the player's mass times that initial velocity squared. I'm going to do some rearranging, so I will multiply both sides by 2 to cancel out the 1/2. So I get 10,000 joules equals 100 kilograms times velocity initial squared. I will divide both sides by 100, and that'll cancel out 2 of the zeros. So I end up with 100 equals my initial velocity squared. Take the square root, and I get the initial velocity of the player is 10 meters per second. Great. One more example. Using elastic, the one we haven't talked about yet, this video. So say a 0.5 kilogram arrow is pulled back to 25 centimeters through a bow with an average force of 4 newtons. What is the spring constant? And remember, spring constant is that weird letter K in that elastic potential energy equation of the bow. Speaking of elastic potential energy, since they said that word spring constant, I can probably assume I'm going to use that elastic potential energy equation because that is the only equation we know of so far that has spring constant even in the equation. And they also gave us force and distance, so I'm probably going to use work. And that work energy theorem is work is equal to any change in energy. What type of energy was gained? You pull an arrow through a bow, it's gaining elastic potential energy. So really, I can replace both of these with their own equations. I know I'm going to use force, so I'm going to use the work equation. And I know spring constant is involved, so I need the actual equation for elastic potential energy. Now I'm going to plug in stuff. Force is 4 newtons. Distance is 0.25 meters. Don't forget to convert. Equals 1/2. Spring constant is what we're looking for. And the displacement the bow is pulled is actually the same distance as what was on the other side, but don't forget to square it. Those of you algebra nerds might recognize that I can actually cancel something out. Since 0.25 is on both sides and it's squared on this side, it gets rid of one of these, but it cancels out completely on this side. So that makes your algebra a little easier. If you don't understand that, you don't have to do that. You can take a step-by-step of rearranging everything. I'm not going to show all of my work, but I will show some of it. So I have 8 newtons on this side equals K times 0.25 if you canceled everything out. If not, you might still have a squared and a 0.25 on the other side, and that is fine. When I divide both sides by 0.25, it's a point, not a negative, I get K is equal to 32, which is the answer down here. Newtons per meter are what we measure spring constant with, and that's basically how strong the spring or the rubber band or whatever we're talking about is. So again, the big idea is this archer did work pulling the arrow back through the bow a distance, and that is now exactly equal to how much elastic potential